Great. So as listed here, the title is From Categories to Curve Counts 2, Variations of Semi-Infinite Hodge Structures. This is part of a joint project with Tim Peretz and Nick Sheridan. Nick spoke yesterday about the first part of the project. And there's an archive preprint up there, and some parts of what I'll say are in preparation. Okay, so I'll use roughly an outline of where we're going. Just at a glance, maybe let me just jump right in. So what's going on here? What do I want to talk about in this talk? I want to talk about relating different types of mirror symmetry. So in the last talk, there were some structural results proved about homological mirror symmetry and some open-closed maps. And today we really want to get into relating different types of mirror symmetry, particularly homological and enumerative. So the idea that there should be such a relationship already goes back to Koncevich's 94 ICM address, where homological mirror symmetry was proposed. And in fact, we're also going to take an approach that's strongly based on ideas of Bronikov and Koncevich. This perspective, which passes through certain non-commutative versions of Hodge structures, has been clarified and developed by many others in the meantime. We've, for instance, learned a lot from reading the large work of Kotsarkov, Koncevich, and Pantev. Okay, so let me just remind you of the geometric setup for our story. So on the A side, we're going to look at an integral Calabi-Yau symplectic manifold. And we're going to fix, for technical purposes, so that we can set up things without too much effort, a simple normal crossings divisor representing the symplectic form omega. Okay, and this is going to give us a set of coefficients, which I'm going to call K sub A. So in this talk, we're going to be much more concerned about what coefficients we're using and comparing coefficients. So K sub A is going to be some version of the Novikov ring, but in this integral case, we can really work with Laurent polynomials in a variable capital Q. Okay, so we could think of our resulting invariance as being defined over a suitable formal disk, formal punctured disk. Okay, so on the B side, we're going to look at, the candidate mirror is going to be some connected family over a formal punctured disk. And here I'm going to think of the ring of that formal punctured disk as Laurent polynomials in a different variable Q. It's going to be important for the purposes of this story to not a priori identify the two formal disks. Okay? And as before, I want to assume that this is a maximally unipotent monodromy situation, which is to say that this family is somehow maximally degenerate, in a manner that's been much studied in classical mirror symmetry. Okay, so the running example, I want to, right away talk mostly just about one example, and that's the quintic threefold, which is one of the classic examples in mirror symmetry. So here we're going to look at on the symplectic side, the Fermat quintic in CP4, and we're going to fix the divisors coming from the unions of the coordinate hyperplanes and look at the symplectic form that's Poincare dual to that union of divisors, and we'll get a coefficient system, again, Laurent polynomials in capital Q. Now the mirror is going to be a well-known mirror family. It's going to be some resolution of a quintic modulo group action. So we'll take this particular quintic, the zero locus of negative z1 times up to z5, plus q times the sum of zi to the fifth power. So this is some hypersurface in projective space over this field. And we'll mod out by some group action, which essentially comes from root of unity actions on the various coordinates. Okay, so this is our running example. When we say x to the fifth, y to the fifth, we mean this pair. Okay, so any questions so far? So let's talk about enumerative mirror symmetry. What do we mean for the purposes of this talk? Of course, enumerative mirror symmetry is much more broad than what I'll say here. One part of the enumerative A model is this series n sub d, where n sub d is the number of degree d rational curves on the quintic. So this is a well-known series. N sub 1 is 2,875, n sub 2 is 609,250, n sub 3 is that number there, and so on. And we want to think of this as being packaged into some generating series in this field, Laurent polynomials in Q. In particular, we want to interpret the counts as a certain Yukawa coupling, which is a symmetric 3-tensor on the cotangent sheaf of the formal disk. And what is this Yukawa coupling? This Yukawa coupling is nothing more than a 3-point genus 0 Gromov-Wood invariant of the hyperplane class with itself. Okay, so modulo this sort of usual multiple cover story and so on, one can expand this 3-point genus 0 Gromov-Wood invariant as some formal series in Q containing this enumerative information. Okay, on the B model, we want to look at periods of differential forms. So in particular, we're going to similarly define a B-side Yukawa coupling. It's another power series in Laurent polynomials in little q, and it's defined by integrating some derivatives of the volume form, of a suitable holomorphic volume form. Okay, so what does the enumerative mirror symmetry prediction in this situation? The prediction is that there should be an isomorphism of punctured formal disks called the mirror map that intertwines the Yukawa couplings. Okay, and moreover, it's not just that there should be an abstract isomorphism, it predicts an explicit formula for this isomorphism. Okay, so in particular, in this case, we know this formula classically. Big Q is sent to little q plus some higher order terms, some transcendental series. I'm not going to get into what it is specifically. Okay, what's the point of this prediction? Well, on the B side, the Yukawa coupling can be computed very efficiently in terms of solutions to Picard-Fuchs differential equations. And so this actually leads to predictions for the numbers n sub d, which a priori were quite hard to compute. Okay, so this was the observation in this landmark paper of Candelas, de la Osa, Green, and Parks, and it was proved in 1996 by Giventhal, Lian, Yu, and Yao. Okay, in these examples and many more. Any questions about what enumerative mirror symmetry is for our purposes? Okay, so let me remind you what homological mirror symmetry is for our purposes. So let's say we have a pair x and y as before. Again, for x, we've fixed this system of divisors. So we say that x and y are homologically mirror if there is a map of these formal disks, an isomorphism of these punctured formal disks, that over which there's a quasi-equivalence of A infinity category. So we use this map on the level of fields to pull back the derived category of coherent sheaves of y so that it lives over the same field as the Fukaya category does, and now we would like that there be some quasi-equivalence between a split closed derived Fukaya category and a DG category of coherent sheaves on the mirror. So this version of the Fukaya category, which depends on this additional system of divisors D, is called the relative Fukaya category and was discussed in Nick Sheridan's talk yesterday. I'm not going to give details on it again, but it's some version of the Fukaya category that you can define in this setting. Okay, so one of the key takeaways from yesterday's talk was that under some core homological mirror symmetry hypotheses, so let's suppose we've just matched up some subcategories on either side, enough to produce an embedding of coherent sheaves into the Fukaya category. Under those hypotheses, actually this equivalence will hold. So this equivalence comes not entirely for free, but a little bit more easily than we might have thought. So let's go back to our running example of the quintic threefold and its mirror family. It's a theorem of Sheridan's that, in this case, x and y, as given above, are homologically mirror. That is to say, for some undetermined mirror map, so some quasi-equivalence of formal punctured disks, we don't know what it is to order 2 and higher. We know to order 1, it's plus or minus, it's plus or minus the identity map. So for some undetermined map like this, the pullback of the derived category of coherent sheaves is quasi-equivalent to the split-closed derived Bukai category. Okay, so the natural questions we might ask following proposals of Kontsevich and Veronica-Kontsevich are the following. So the theorem itself doesn't tell us what C tilde is. It just proves that some C tilde must exist, okay, by some deformation theory argument. So you might ask, does it agree with the standard known mirror map in this case? For which there's a prediction about what it should be. The second question we might ask is, does this statement imply, without any further computations, enumerative mirror symmetry for this pair x and y? And the third statement maybe is more about the equivalence of categories itself, but it follows from the same techniques. This equivalence given is an equivalence of A-infinity categories. But for the purposes of non-commutative geometry and topological field theories and so on, the natural thing to study are Calabi-Yau categories. So one might ask, what do we know about equivalences of Calabi-Yau categories? Is this equivalence, does it enhance to some sort of equivalence of Calabi-Yau categories for some intrinsic Calabi-Yau structures? So the theorems I want to talk about are answers to the three questions. So the answer to the first question is yes, C tilde agrees with the standard mirror map. The answer to the second question is also yes, the statement implies, without any further computations, enumerative mirror symmetry. And the answer to the third question or remark is, in fact, in this setting, mirror symmetry, homological mirror symmetry can be canonically enhanced to an equivalence of Calabi-Yau categories. Okay, so I'll talk more about the first two, and then, time permitting, I'll say something about the last point. Okay, I should probably immediately issue some remarks and caveats / disclaimers. So first of all, the proof of this theorem goes via showing that homological mirror symmetry implies yet a third form of mirror symmetry called Hodge-theoretic mirror symmetry, which is also classical, and the idea that this implication should hold is due to Baranikov and Kontsevich. And then the disclaimer is that the result, as we stated in the previous slide, is actually contingent on a conjecture that's purely on the B side. So even without that conjecture, which would allow us to use Picard-Fuchs equations to make the final predictions, we actually can still conclude that the derived category of coherent sheaves knows in a canonical way about genus 0 Gromov-Witten invariants.
So you don't need Calabi-Yau structure?
We need some form of Calabi-Yau structure for this. No, you actually do. Implicitly, you're fixing a Calabi-Yau structure to get this. But actually, I think the statement is that the derived category of coherent sheaves has an intrinsic choice of Calabi-Yau structure, so you don't need to specify it as initial data. One interesting, yes.
So the general rule is that you reduce these invariants to the Calabi-Yau structure as incompatible of the Marshall structure.
Yes.
And then you presumably to match up the splittings with the surface of the Marshall equation.
Right. So I think that is the yoga if one wants to extract, say, general Gromov-Witten invariants. So I think Kevin was asking, maybe I can try to repeat your question. The general yoga for this TFT approach to recovering Gromov-Witten invariants is you need an equivalence of Calabi-Yau structures along with a certain splitting of the non-commutative Hodge filtration. So are we matching up these splittings? So the answer is, first of all, our approach actually does reveal that there are canonical splittings on either side. I don't think we're fully matching them up, but I think there's enough of this. I mean,
well, it's given by the non-commutative filtration.
yeah, no, okay. So there is a. Sorry, I understand what you're saying now. Of course, there is one that's entirely determined. Yeah. So the splitting is actually given from homological information. Yeah. Thanks. Yeah.
Well, on the B side, it seems this
Sorry, what?
Gamma class story is also.
Oh yeah, so I'm not going to go anywhere near that, but there are lots of interesting questions that are beyond what's in this result, including the integral structure in mirror symmetry and so on. Yes, so actually, to answer your question, absolutely. We do get, that the splittings match up. What we don't necessarily get is that the compatibility of these splittings with pairings match up, which you would also need to recover higher genus from. Okay, so let's formulate Hodge-theoretic mirror symmetry, which is the key intermediate step. Okay, so we're going to use a version of this due to Barannikov. And we'll start with defining a pre-variation of semi-infinite Hodge structures. Okay, over some base, which we should just think of as a formal punctured disk. So what is this? It's the data of a sheaf over this punctured disk, equipped with a filtration, which you should think of as being like the Hodge filtration. Should be equipped with a flat connection that satisfies Griffith's transversality with respect to this filtration. So it looks a lot like a variation of Hodge structures at this point. And it should be equipped with a covariantly constant pairing that behaves well with respect to this filtration. I won't go into the details about that. But maybe I should say that this is often what's called a polarized pre-variation of semi-infinite Hodge structures, where the pairing is often called the polarization. Okay? For the purposes of this talk, I'll just call it a pre-VSHS, VSHS, and assume that the polarization comes along for the ride. Now, that's what a pre-variation of semi-infinite Hodge structure is. What about a variation of semi-infinite Hodge structure? In that case, the sheaf should actually be a vector bundle. And this pairing should actually be a non-degenerate pairing. Those are the two things we need to really say that we're talking about a variation of semi-infinite Hodge structures. Okay, so there are natural examples on both the A side and B side. So let's talk about the B side first. That's a more classical story. Let's say we have a complex family over a formal disk, as before. Then we can associate the classical variation of Hodge structure, and that is an example. So what that means is the vector bundle that we look at is the family of cohomologies of the fibers. The filtration on this vector bundle is the actual Hodge filtration. The connection is the canonical Gauss-Bonnian connection that exists whenever you have such a situation. And this pairing up to some constant is the integration pairing. Okay, let's talk about the A model example, which is also well known, but maybe not quite as classical as the B model example. So here we're going to have something quantum. So what is the vector bundle? It's actually a trivial vector bundle. It's just a cohomology of the total space of your symplectic manifold with coefficients in Laurent polynomials in Q. Okay, the filtration is also not a very interesting filtration. It's just a degree filtration on cohomology. I would say the pairing also is, maybe the standard pairing on cohomology. It's just the integration pairing up to some overall sign. The really interesting part of the story in the A model is this connection, which is the quantum connection. So this connection, to differentiate by some vector field q d by dq, a class, you just differentiate the cohomology class, but then you add a quantum term. This is the quantum cup product with the symplectic form. Okay, so this involves some counts of J holomorphic spheres. Flatness at this point is a fairly non-trivial property to check, but it holds, and so you get this A model variation of semi-infinite Hodge structures. Yeah, so that's my next comment. There's nothing semi-infinite at the moment, and there really won't be for my talk. I think it's just a convenient language. Absolutely. Yeah, maybe I should say that right now. No, that's not the next page. So actually, in the Calabi-Yau Z-graded situation, these are all really traditional. They're classical variations of Hodge structure. There's nothing semi-infinite about this, except the structures that arise non-commutatively and in our story are actual semi-infinite structures, and our main technical results hold in much more generality outside of the Calabi-Yau setting. So it was a convenient language to use, even though it's not more general in this case. Okay, so I've said what a variation of semi-infinite Hodge structure is. What's an isomorphism of variations? Well, it's just a map between the associated vector bundles that lives over some isomorphism of formal punctured disks. And this map needs to intertwine all of the variation of Hodge structured data. So it should be a filtered map, it should preserve connections, it should preserve pairings. Okay, so using that we can define what it means for a pair of spaces to be Hodge theoretically mirror. Remember, on the previous page, we defined natural A model and B model variations of semi-infinite Hodge structures. So we say that X and Y are Hodge theoretically mirror if these associated A and B model variations are isomorphic. Okay, so now we come to this crucial fact that's classical, but kind of really helps us get off the ground here. The point is, one of the reasons to use the Hodge theoretic formulation is that if you have a variation of Hodge structures of the correct type, for instance, one associated to a maximally unipotent or a maximally degenerate complex family, it determines canonical coordinates on the base punctured disk. So a priori, this formal disk had lots of different coordinates. There was some huge infinite space of coordinates, but using Hodge theoretic data, you can fix a canonical coordinate up to some C-star scaling. And that has strong implications. It implies that if you have an isomorphism of variations of semi-infinite Hodge structures that lives over some map, some isomorphism of formal disks, you might think that that isomorphism could be completely arbitrary, but in fact, it's constrained. Since there's a canonical coordinate determined by Hodge theoretic data, this map has to intertwine, it has to match up these canonical coordinates. So this map of punctured disks actually fixed up to some C-star scaling potentially. Okay, so this is the key input into our story that we're going to be using. Any questions about this?
Do you need the integral structure?
To fix the C-star scaling, maybe you do. I don't know. You don't need an integral structure for canonical coordinates. I mean, I think maybe if they're higher dimensional bases, the integral structure can really help. But we're working with one-dimensional bases. You don't need an integral structure. Okay, so the key point here is that for Hodge theoretically mirror pairs, the corresponding mirror map, the isomorphism of formal disks, is actually uniquely determined up to this complex one-dimensional ambiguity. Okay, there's another aspect of this that we want to use, and that's, well, first of all, there's a notion of a volume form for a variation of semi-infinite Hodge structures. And this is just a non-vanishing section of the bottom piece of the filtration of this vector bundle. Okay, so it's just some section of the vector bundle that lives in the bottom piece. So for instance, in the B model, it's going to be some non-vanishing section of the top exterior power of the cotangent sheaf. So if such a volume form exists and this rank of this group is 1, then there's still a K-star ambiguity in choices of volume forms, of nowhere vanishing volume forms. One of the things that Hodge structures allow us to do is it allows us to determine some unique, up to again C-star, Hodge theoretically normalized volume forms. So we can use these variations of Hodge structures to fix a unique choice. In particular, we talked about Yukawa couplings earlier, and they were determined by covariant differentiation and integration with respect to a volume form. Since we have a canonical choice now, the variation of Hodge structures also determines in some canonical fashion Yukawa couplings and other enumerative variants. Okay, so actually, maybe I should just repeat this. The point is, I'll draw a picture just to keep in mind. So here we have enumerative mirror symmetry. Here we have Hodge theoretic mirror symmetry. And to be discussed, homological mirror symmetry. And enumerative mirror symmetry is saying that there's some isomorphism of formal disks that sends that intertwines the Yukawa couplings. Okay, Hodge theoretic mirror symmetry says that there are some isomorphism of variations of semi-infinite Hodge structures. And what we've been arguing is this classical fact that if you have an isomorphism of Hodge structures, it may seem like it's not enough information, but it actually is. You can fix all of the ambiguities. Okay, so let me now state the main theorem. Let's say we have a pair x and y as before. So x is a symplectic integral Calabi-Yau with a divisor. Y is a mirror Calabi-Yau family. The main theorem is that let's say that x and y are homologically mirror in the sense that the split closed derived Fukaya category is quasi-isomorphic to the DG category of coherent sheaves, where we've done a coordinate change by some unknown isomorphism of formal disks. Then it actually follows that x and y are Hodge theoretically mirror over the same unknown map. Okay, so as a corollary, now we can appeal to Hodge theory.
So this does not require that the equivalence respects Calabi-Yau structures.
In fact, it will follow that the equivalence. So I think
You will not put it as an assumption.
we will not put it as an assumption. So it follows as a corollary that, well, if we have an isomorphism of variations of Hodge structures over this map of formal disks, that map must preserve canonical coordinates. Okay, and now that determines it up to a C-star ambiguity. I want to point out that in Sheridan's result, the leading order term of this isomorphism was actually computed to be plus or minus 1. So in fact, this map, C tilde, is actually determined up to overall sign, which then itself can be fixed. Okay, so it follows that the A and B model Yukawa couplings agree. And it also follows, through similar methodology, that homological mirror symmetry refines to an equivalence of saturated or smooth and proper Calabi-Yau categories for intrinsically chosen Calabi-Yau structures on each side. Okay, so how do we pass from homological mirror symmetry to Hodge theoretic mirror symmetry? That's kind of the key point. Okay, so well, there's an old idea of how to do so. The point is, whenever you have an A infinity category, you can naturally associate. So if the A infinity category is over some, for instance, Laurent series field, you can associate a natural variation of semi-infinite Hodge structures. Okay, so how do you do this? Actually, a priori, it's only a pre-variation. Okay, so how do you do this? What's the sheaf you assign over the formal disk? It's the periodic cyclic homology together with its non-commutative Hodge filtration. Okay, what's the connection? Well, there's a connection on periodic cyclic homology over some Laurent series ring that was written down by Getzler in 1993, and so we want to use the Getzler's Gauss-Manin connection. So there's some very explicit formula for this. Okay, the third thing is, what about the pairing? Well, Shklarov in 2013 wrote down a higher residue pairing. He wrote it on negative cyclic homology, but you can adapt. It naturally gives a pairing on the periodic cyclic homology of this form. And it's going to satisfy all the axioms of a previous HS if C has a weak Calabi-Yau structure. So there's this pairing that exists always, but it might not be.
I think it's Calabi-Yau superlative.
I think symmetric requires.
Symmetry is right.
That's all I mean. So I didn't. That's right. I didn't say it in the axioms, but we want to assume symmetric. It doesn't really matter, but I agree. So this exists always, and then weak Calabi-Yau implies symmetry. Okay, and so moreover, this is actually a Morita invariant. Okay, so if you have a quasi-equivalence of, split closed derived categories, this data is preserved. Okay, the categorical data is preserved. I should say, furthermore, if you knew some more, so the category had to be proper, which is to say the cohomology morphism spaces have to be finite rank over K to get this off the ground. But now if you're interested in this actually being a variation of Hodge structures as opposed to a pre-variation, if the category is homologically smooth and the non-commutative Hodge-Durand conjecture holds, which is to say a certain non-commutative Hodge spectral sequence degenerates, then this is actually a variation of semi-infinite Hodge structures. Okay, so I've made some references to where these structures appear, and Nick Sheridan's put out a preprint very recently explaining formula for all of these with uniform conventions along with an explicit proof of Morita invariance. So I'd encourage you to look there for more details. Okay, so I guess this is the remark I made earlier, that really for Calabi-Yau Z-graded situations there's nothing semi-infinite, so I'll just skip this. Okay, what's the proof using this information? So here's an outline. I'll just write this on the board as well because I... Okay, so at the top, we have these categorical variations of semi-infinite Hodge structures. And because of Morita invariance, they're isomorphic to each other, okay? Associated to the Fukaya category in coherent sheaves. I mentioned that our result is reliant on a conjecture. I'll explain that in a second now. The point is that there's a natural map of bundles with filtration from the periodic cyclic homology of coherent sheaves to the B-model variation of Hodge structure. It's not completely known whether it preserves all of the relevant data. A posteriori, we know it, but it's not completely known beforehand, so I'll explain that in a second. And our main input is on the A side of the story, where we construct an isomorphism to the A-model variation of Hodge structure. Okay, so let me talk about the B side a little bit. So we have known for quite a while that there are filtration-preserving isomorphisms that go from the periodic cyclic homology of coherent sheaves all the way to the Durand cohomology, okay, with its two-periodic grading. They pass through an intermediate entity, the periodic cyclic homology of the scheme, and so the combination of these two isomorphisms is the isomorphism we're interested in, and it's due to Keller and Weibel respectively. And as usual, to ensure compatibilities with structures, we maybe want to modify this by a Todd class contribution. I don't want to say too much about that.
There are many isomorphisms that come with bit.
Sorry, what?
There are many isomorphisms in principle. Yeah.
Yes, there are many isomorphisms. That's right. Absolutely. So we have some choices of isomorphisms, and we want to choose the ones described in the literature with this modification. Okay, so the main conjecture that isn't known at the moment is that this map from this categorical, vector bundle with filtration to this vector bundle with Hodge filtration intertwines the Getzler-Gauss-Monine connection, which is defined on periodic cyclic homology, with the usual Gauss-Monine connection.
Maybe Maximo correctly, but doesn't this follow from the boundary theorem?
Yeah, no, but yeah, really work it out. It's comparison. It's comparison.
I mean, actually,
some kind of Bill Vickers.
yeah. So
this is mentioned here.
I mean, we know a fair bit more about what's missing. So basically, there is a version of the formality theorem for the cyclic HKR map, and it's so we know that we have that, and we know that in the smooth category, or in some sort of local setting, we have compatibility with connections, but there's a globalization story for this compatibility with connections that is not in the literature currently.
Oh, so
Yeah, so in the smooth setting, we have, for C infinity of x, we know this. Okay, and the next bit of the conjecture is that this map intertwines pairings, and I should point out that Nick Sheridan in part 1 of this series explained that on the associated graded, this is known to hold. Okay, so by work of Markarian and Rodriguez. Okay, so let's talk about the main technical input into this theorem. So firstly, it's a theorem due to me and adapted to the compact Calabi-Yau case by in joint work with Peretz and Sheridan. Also separately, I understand it's due to Fukaya Ota Ono, constructing an actual map between these filtered bundles. Okay, so there's a filtered map called tilde OC from the periodic cyclic homology of the Fukaya category to this cohomology of x with coefficients in Laurent polynomials. We call it the cyclic open-closed map. And by a standard comparison argument using spectral sequences, it's an isomorphism whenever the associated graded map, which we call OC, is. So Nick talked about this OC map from Hochschild homology to the cohomology of x, and the map we construct is an isomorphism whenever that associated graded map is. So as a corollary of the last talk, under homological mirror symmetry hypotheses, in fact, this map is an isomorphism. Okay? So why is that? Let's just remember what Nick talked about at the very end of his last talk. One of the results of Peretz and Sheridan imply that whenever there's a homological mirror symmetry situation here, there's a so-called non-degenerate subcategory of the Fukaya category. And then some compatibility with module structures and Mukai pairings due to us and Abuzaid, Fukaya, Ota Ono imply that in fact, therefore, the associated graded OC map is an isomorphism. So by what we've written here, this map is too. I want to make a remark at this point. So we've been needing to assume that to get a variation, an actual variation of Hodge structures instead of a semi-infinite variation, we've been assuming that the non-commutative Hodge-Durand spectral sequence degenerates. Now, it's conjectured that that's always true for a smooth proper category, and there are proofs in special cases by Kaledin, and then by reduction to commutative case, classically on the B side, this actually gives a proof on the A side whenever this map is an isomorphism, because the filtration on the cohomology of x is some very stupid filtration, it equals its associated graded, that implies that the filtration on periodic cyclic homology is itself, that it's itself trivial, so it's isomorphic to its associated graded. Okay, so in this case we realize that the non-commutative Hodge-Durand degeneration conjecture holds for the Fukaya category. Okay, so I should say what our main input is into this story. So we have this map, this cyclic open-closed map, and our main theorem is that this is a morphism of pre-variations of Hodge structures. That is to say, it intertwines connections, the A-model connection with the Getzler-Gauss-Manin connection, and it intertwines pairings, the integration pairing with Shklerodov's higher residue pairing. Okay, so the corollary of the last slide is that actually this map is now an isomorphism of variations of Hodge structure. So the Fukaya category, in fact, knows the A-model variation of Hodge structure. So just one remark, the statement that this is a morphism of variations of Hodge structure, one of the parts of that statement is that it intertwines certain pairings. If you look at the associated graded version of that statement, we recover a statement that Nick talked about in the last talk, which is that the map from Hochschild homology to quantum homology respects pairings. The next thing to say is actually, for the purposes of setting up holomorphic curve theory, we're going to use a version of variations of Hodge structure that passes through the Riesz correspondence. Instead of thinking about periodic cyclic homology, we want to think about negative cyclic homology, which is in some sense the sum of all the filtered pieces with this K join U module action that is given by inclusion of one filtered piece into the next piece, and we want to sort of state everything there, and that's what's going to happen in our paper, or that's what happens. Okay, how much time do I have? Maybe what I'll do, so I'll make some remarks about why the result should hold first. So compatibility with connections, I would say, is the most technically involved part of the story in terms of the guts of the holomorphic curve theory. But here's one reason it should hold. So on the associated graded, we understand that differentiating with respect to q d by dq, this vector field is actually contraction with a categorical Kodaira-Spencer class that Nick Sheridan talked about last time. Moreover, in part 1 of the series, that when Nick talked yesterday, he showed that the categorical Kodaira-Spencer class is actually CO of the symplectic form. And we know before this result that OC is a module map. Hence, the cat product of a Hochschild chain with this categorical Kodaira-Spencer class is actually sent to the quantum product by compatibility of OC with module structures. So on the associated graded, the compatibility with connections follows from compatibility with module structures. Though to make the statement at the level of periodic cyclic chain complexes is significantly harder. Okay, and compatibility with pairings I already talked about. So I wanted to either give a few details about the cyclic open-closed map or talk about Calabi-Yau structures. Maybe I'll jump ahead to Calabi-Yau structures first and then come back to this if there's time. Okay, so maybe, so one of the other results I stated is that there's a canonical equivalence of Calabi-Yau categories. So maybe I should say what a Calabi-Yau structure is. So we're going to use a version of this definition due to Kontsevich and Soibelman. So if you have a proper A infinity category, a strong proper Calabi-Yau structure is a morphism of degree n from the positive cyclic chain complex of your category to the ground field, which is non-degenerate, and non-degenerate just means that there's a suitable form of Poincare duality if you look at the associated pairings between Hom groups, between Hom xy and Hom yx. One of these should be Hom star and one of these should be Hom n minus star. There's a typo there. But if you multiply and you end up in Hom n xx, and then you map this into positive cyclic chains and then to K via this map, we should just get the usual perfect pairing from Poincare duality. Okay, so it's some refinement of that. Kontsevich-Soibelman proved that in characteristic 0, such a structure gives you a quasi-isomorphism to a cyclic A infinity category. So if you like cyclic A infinity categories, you can think in characteristic 0 that that's what we're talking about. And so it's a theorem due to me in this sort of setting, and then adapted to the relative Fukaya category in joint work with Peretz and Sheridan, that the Fukaya category has a canonical strong proper Calabi-Yau structure. I should also say Fukaya proved that in a different construction of the Fukaya category, you can set it up with a strictly cyclic structure over the reals. Okay, so in our case, we actually know some more information. We know that our Fukaya category and coherent sheaves are smooth and proper. They're not just proper, they're homologically smooth. And so there's a corresponding strong smooth Calabi-Yau structure in the sense of Kontsevich and Vlasopoulos. You should think of it as some sort of non-degenerate element of the negative cyclic chains of the Fukaya category. I don't want to say what non-degenerate means in this setting just because there's not time, but it's a certain nice element. And I want to point out that both the canonical, proper Calabi-Yau structure and the smooth Calabi-Yau structure, which are essentially equivalent data in this case, they can both be defined in terms of the cyclic open-closed map. So you can use this map to nail down what the structure is canonically. And our main result implies that as thought of as an element of periodic cyclic homology, or as of a filtered part of periodic cyclic homology, this non-degenerate element actually corresponds to a Hodge theoretically normalized volume form. Okay? In the sense that I talked about earlier. So that actually immediately implies the following theorem. It implies that the equivalence between the split-closed derived Fukai category and coherent sheaves preserves a certain pair of strong, smooth and proper Calabi-Yau structures, where we use this sort of canonical Calabi-Yau structure in the Fukai category that's constructed with holomorphic disks. And on the mirror side, we use a Hodge theoretically normalized Calabi-Yau structure, which we get from the geometry because we have these Hodge structures sitting around. We don't need to appeal to the symplectic side or pick it out of air. And so in particular, in the sense of Costello or Kontsevich-Soibel, we get an equivalence of associated topological field theories, again, controlled by open moduli space at this point. Not compactified, open moduli space. So maybe I'll stop there and take questions. Thank you very much.
Questions?
Next week's Calabi-Yau. Can you say a little bit more about what the assumptions are?
C1 equals 0, and I mean integral symplectic form, Calabi-Yau. Nothing else really. Sorry, come back. Just come back to Calabi-Yau. Absolutely.
Next term is for Calabi-Yau hypersurfaces.
Yeah. So our theorem is supposing homological mirror symmetry holds for a compact Calabi-Yau. Then we can deduce all of this, and so we can in particular apply it to Calabi-Yau hypersurfaces because we know it holds them.
Didn't quite get so you're saying the compatibility with the model structures, those like this associated with fixed cross structures or multiple and so on. And then you're saying you can regenerate these to say that the actual connections are connection. But is it some order by order analysis and deforming the Higgs bundle back to the connection, or is it
Order by order and U.
like also it's
Yeah,
not
so-
like a harmonic?
No. It's absolutely done by hand, order by U. So you start with the associated graded statement, and that's like the U equals -1 coefficient of compatibility, and you work order by order in U and construct higher homotopes.
It's really about the discretization.
Yes. And it's really involving moduli spaces of disks, parametrizing higher homotopes in U.
Since you also have a compatibility, it's very the Hodge structures that you have. Some TFTs and
Don't you need them to be compatible with, the splitting needs to be compatible with pairing, and there's some extra data
Oh, you
there.
have the pairing.
We haven't, no, we have the pairing, the splitting is compatible with pairing on both sides, but we haven't compared the extra data. So the extra data is sort of some highly non-trivial data. This, maybe not, you would know better than me.
So where you use this Calabi-Yau, I think this holds to the relation you don't need Calabi-Yau.
That's right,
And also this compatibility with pair.
yes.
And how about this compatibility of connections? You don't need it?
You don't need it there either. I think basically to extract out Yukawa couplings, you need a normalized volume form. And as I was trying to say here, the normalized volume form is in some sense equivalent to Calabi-Yau
Yeah. So
choice.
yeah. So the fact that X has a ABD structure just uniquely determine this product. Somehow you need Calabi-Yau.
For what, sorry?
For this ABD category, uniquely knows of this product.
Yes,
In a
yes.
You do need.
For to uniquely know the Yukawa coupling, you do need the Calabi-Yau structure. But the point of this is somehow the Calabi-Yau structure comes from Hodge theory. So you don't need to necessarily, aside from knowing that one exists, you don't need to fix one in advance. It's determined by Hodge theoretic considerations. So
But in the case of this, in this symplectic manifold, it's
Yes.
not Calabi-Yau.
yes.
Then,
So if the symplectic manifold is Fano, for instance,
yeah.
in that case, there's still a Calabi-Yau structure,
Yes,
right?
of course.
Yes, absolutely. And so pinning it down, I think there's still a canonical geometric Calabi-Yau structure.
Yes.
The question is whether you can use these sort of Hodge theoretic considerations to isolate it, and I think you can't. I think that's part of,
We can't.
you can't, that's right,
That's
yeah. Yes?
My understanding is that you match the column.
Yes.
You actually can't.
I think there's a canonical coordinate without using the integral structure. I think that's the point.
It's not like T versus T to R.
Oh, but we're working in Laurent polynomials. We're not working in real powers. I mean, we're assuming we're in a setting where we can define all our invariants over Laurent polynomials with integer coefficients. So that's some geometric hypothesis that we've imposed. So I don't have much to say, at least right now, about the real coefficient.
Makes sense. Can you ask how to follow your case? Since there's defined many parameters, because in syncretic geometry we see that we consider connection with the reverse invariants has only second, first order poles.
Yes.
Yeah, so it's a very rigid structure.
It's very rigid still. I mean, I think it's just
only a few parameters.
there are only a few. I mean, I'm not saying there's an infinite space of parameters. It's only a few, but it's not one-dimensional. Yeah. Okay, thanks again.
Okay.